Welcome back.
Thank you. Thanks to those of you who came back from the coffee break. It's difficult to tear oneself away. So what I want to do now is spend some time with two of the ideas that came up in the course of the arguments that we just gave, specifically the maps in and the maps out. And both of these types of maps are components of important structure on configuration spaces, or their homotopy types, and each is important in its own way. So to begin with, let's talk about the maps in. So if you remember, the maps in required us to make a choice of embedding of some disjoint copies of Euclidean space inside of Euclidean space. And then we use that embedding to push configurations into the larger Euclidean space, right? And I said the evil word just then. I said the word choice. And the good thing to do is not to make a choice, but to make all the choices at the same time. So to do that, let me introduce the notation Cn of k. So what Cn of k is it's the space of rectilinear embeddings of a cube inside of a cube. So the space rectilinear, I'll say what that means in a second, embeddings of a disjoint union of k copies of the unit cube into the unit cube. So the parameter n is the dimension as it has been. The parameter k is the number as it has been. Okay. So what rectilinear means is that all I'm allowed to do is translate the cubes and scale the sides of the cubes, perhaps by different amounts. Okay. So a picture of such a cube is here's my larger, the target n cube, and inside of it I have 3 smaller cubes, 1, 2, 3. Okay. And drawing this picture, because I've declared that only translation and scaling of the sides is allowed, this picture completely specifies the embedding. So these sorts of pictures and the points in these spaces are typically called little n cubes. Is there a question? No. Yes, they're very famous. They're more famous than certainly anyone here. And the exercise, which shows their connection to configuration spaces, is that, well, if I have a little cube, then I can evaluate at the center of the cube, each one of them, and that gives me a configuration. Right? So evaluation at the centers of cubes gives a homotopy equivalence between the space Cn of k and the configuration space of k particles in Rn. Yeah. It doesn't matter.
Oh, sorry. I can ask it again for everyone. Is there a restriction that the cubes aren't allowed to touch each other?
Oh, I thought I understood. I think I understand. I think you're asking,
Like, can they
can't-
crash? Can they overlap?
Can they touch each other? They
Yeah.
cannot overlap. The way I've defined it, these are open cubes. The picture does not make that super clear, but sometimes I want to write like dashed lines to mean something else. That's why the lines are solid. There is no boundary to touch other boundary, but they certainly cannot overlap. Does that answer your question? Okay. The condition is that it be an embedding of the disjoint union, and so that in particular means that the map is injective.
Can I ask a question?
You may.
You said that you only translate or scaling the cubes, but the picture shows a rectangle.
So I said that you translate the cubes and you may scale each side separately.
Each side. Okay.
Yeah.
Thank you.
Other questions? Okay, so the homotopy types of these spaces are familiar. They're the thing that we've been studying for a while. On the other hand, they carry extra structure. So these spaces carry extra structure. In the form of composition maps. I can compose embeddings and get embeddings. So earlier, what we said was choose an embedding of some number of cubes in, and then you could put a configuration in each cube. It's the same thing here. So I choose an embedding of some number of cubes, k of them. That's my my sort of larger framework. And then inside of each of those k cubes, I get to put some number of other cubes. So for each 1 up through k, I get some number of cubes. So L1 cubes, L2 cubes, up through Lk cubes. And then when I compose those embeddings, what I get is L1 plus L2 plus through Lk cubes. See, n. If you wanted to axiomatize this kind of structure, which you would if you were Peter May, then what you would do is you would invent operads. So, so this structure is axiomatized as an operad. But you shouldn't think that you need to understand what operads are in order to understand this. It's the other way around. In order to understand what an operad is, you just have to look at these, and then you will know what an operad is. I'm completely genuine. You might disagree with me if you are an operads person, but I'm sorry. Yeah. Okay. Great. So operads are a whole thing, and there is a rabbit hole that we could go into. So here's the rabbit hole. Here it is. The rabbit is over here. I don't really know how to draw a rabbit, but we'll say that that's the rabbit. And inside of the rabbit hole, there are things like iterated loop spaces, structured ring spectra, embedding calculus, factorization homology, formality, graph complexes, and lots more things. It's a deep rabbit hole. And you could, I could not, because I'm not an expert on all of these things. I'm just a dabbler. You could give a 6-hour mini course on any one of these topics. That's not what I'm doing. I'm talking about configuration spaces. So this is all I'm going to say about operads in any kind of formal sense. If you want to talk about operads or any of these other things, the gossip that I know about these things, please find me after the talk. But this maps in structure is important in another way for our more humble algebra topological goal of calculating homology. One thing that it gives us, oh, and I guess I should probably say a few names before I completely move on. So it's already been said, but Peter May defined the little cubes operad and proceeded to apply it to iterated loop spaces, and building on work of Boardman and Vogt. So, so that's the name to check out. I doubt that anyone in this room didn't already know that, but just in case you didn't know that, it would be remiss of me not to say. So one relevance of this structure to what we already talked about is you can use just these maps, not knowing anything about operads per se, to show that grafting of trees, the homology classes defined by trees that we talked about yesterday, is a linear operation. So we wanted to prove the general Jacobi identity on trees by reducing it to the case of a tree with 3 leaves. And you can do that, and the way to do it is using these maps. So grafting trees is linear on homology because it comes to us from a map of topological spaces. Another relevance of these maps in is that they give us what are commonly, they give us an example of what is commonly called a stabilization map. So these maps also give us what's referred to as a stabilization map. So I can take my configuration of, I'm going to talk about unordered configurations. I can take my configuration of 3 particles. I can shrink them ever so slightly, practically not at all, and I can squeeze a tiny little cube way over toward the boundary and put another particle there. And so then I will be left with basically my original configuration and a new particle very far away. And then I can do that again, and I can do it again, and I can do it again. Okay, so this is a map that I'll call sigma that goes from bk of Rn to bk plus 1. Sigma for stabilization.
So is that related to the scanning map?
Yes is the answer. Yes. It is not the scanning map, but it is related to the scanning map. I don't know what the Siegel stabilization is. I'm sure it's the same thing. So I'm sure that's also true. I know it is the theorem of Macduff, but okay, great. I'm sure it's Siegel also. Other questions or names that should be said?
Oh, sorry, I don't understand how that maps come from those opera maps.
Yeah. So I said it out loud, but I didn't actually indicate it in pictures. So let's adopt my convention of solid lines for the larger box. And maybe it'll be easier to see, or maybe it won't be easier to see. I don't know. What I said was you choose one cube that is almost the same as your whole original cube. And you embed these 3 into that cube. And then you choose the other cube to be way over at the edge. And you put the new particle there. Does that help? Okay. Yeah, totally there are choices. Yeah. I agree. Basically, there aren't choices, but there are literally choices. Yeah. Other questions? Okay. Great. So the stabilization map. The same idea works for open manifolds. So you can squeeze the manifold into itself using a Collar neighborhood of what would be the boundary if you compactified it with a boundary, and you can put a new particle near the boundary. Okay, so as long as your manifold is open, you can do this same thing. And it is good, instead of viewing this as a map for like as a sort of a chain of spaces, one way to think of this is to lump all the spaces together, as I think we did yesterday. We can view sigma not as a sequence of maps, but as a map from this space to itself, an endomorphism of this graded space, a degree 1 endomorphism of this graded space. So sigma is a degree 1 endomorphism graded space. And theorem of Arnold in the case of Euclidean space, and I have been informed that I should write Sequel. I was going to write McDuff, but I will write McDuff and Sequel. Is that if my manifold is connected, open, of dimension at least 2, then this stabilization map it eventually induces an isomorphism on homology. Oh, excuse me. I said that too soon. What I meant to say was something else. That's true, but it's not what I meant to say. The homology of this sort of total configuration space, we're viewing this as bigraded. It has homological degree here and cardinality degree internally. And the stabilization endomorphism preserves the homological degree and increases the internal degree, right? And so, well, a thing with an endomorphism is the same thing as a module over the polynomial ring on one generator. And so we can view this as a graded module over a graded polynomial ring on one generator in degree 1. And the statement in this framing is that this module is finitely generated over that ring. Finitely generated module over the polynomial ring generated by the induced homomorphism sigma star. Of course, none of these people said it this way. And the reason that finite generation is interesting is there's structure theory, as many of you probably know, due to Hilbert, about graded modules over graded polynomial rings. So if I have a finitely generated graded module over a polynomial ring on some number, say d of generators, then it has what's called a Hilbert polynomial, which has degree at most d minus 1, number of generators minus 1. And its dimension, or its dimension in particular degree, is eventually equal to the Hilbert polynomial, which is a polynomial in the degree. Okay. And so if we apply that here, the number of variables of the polynomial ring is 1. So number of variables minus 1 is 0. And so if I fix the homological degree, what this is saying is that the dimension over field of of, so in other words, the Betti number is eventually equal to a polynomial of degree 0, which is, in other words, constant. So as a corollary, we have what's called homological stability, which is, this is how those people actually phrase this. Which is that for a manifold as above, the dimension of hi, sorry, I should have said that this is finitely generated in each degree, each homological degree. I guess I'm grouping all of the homological degrees together. The dimension of the homology unordered configuration space with whatever field coefficients you want is eventually constant. As a function of k, the number of particles. Okay. So in other words, as I increase the number of particles, the Betti numbers eventually stop changing. Thus stability. Maybe I'll pause at this moment to see if there are any questions.
Anybody has a question online? Apparently not.
Okay. So, so these are sort of some slightly vague gestures at some of the import of the maps in. As for the maps out, they are also important in related ways. So I'd like to tell you about some of those ways. So what are the maps out actually? So what the maps out are is if I have a configuration of k particles, then anytime I can write k as a sum of some number of numbers, but let's stick with 2. I can write k as a sum of 2 numbers, say a and b. Then I can split the configuration x1 through xk into first a configuration of a many particles and then a configuration of b many particles, right? So a plus b is equal to k here. I'm going to call this map SAB. And it goes to the product of 2 different configuration spaces. And what it does is it takes this tuple and it just puts parentheses, 2 parentheses in it. So the first configuration is x1 through xa, and the second configuration is xa plus 1 through x. Okay. So here, let's be. I have such a map anytime I can write k as the sum of 2 natural numbers. So what's true about these maps? Let's think about what are some features of these maps. So these maps are, well, on the one hand, the symmetric groups are acting everywhere, right? And this map is equivariant in the sense that in the only sense possible since 2 different groups are acting. So here what's acting is sigma A times sigma B, which is a subgroup of sigma K. And this map is sigma A times sigma B equivariant. So the action sigma A times sigma B. there's another thing that we can observe. So if I can write K as the sum of 3 numbers, A, B, and C, say, so the configuration space of A plus B plus C many points, then I have choices in what I do, right? I can split the first A particles off. Oh, sorry. So this is the splitting map S, A, comma, B plus C. And then I can split the final B plus C many points. Or I can do it the other way. I can split off the last C many points. And that split the first A plus B many points into A and B. And clearly this diagram commutes because both composites are just re-parenthesizing in the same way. Okay. And if this deserves to be called anything, it deserves to be called co-associativity, surely. Because if you read the diagram backwards, it's saying that sort of a binary thing and then another binary thing is the same as doing the binary things in the other order, which is associativity. They're also co-unital in the reasonable sense. So maybe I'll invite you to think about what that would mean. And they're also kind of co-commutative. But also a different way you could say that is they're not co-commutative. So let's see what that means. Well, what could we do? We could take A plus B many points, and we could split them into A many points and B many points. Right? Okay. Well, we could also just change our mind about what A plus B is and say that A plus B is B plus A. Those are the same numbers, right? So we could say this is F B plus A, and then we could split them apart like this. And these are the same space practically, they just differ by a twist, by switching the factors, right? And this diagram doesn't commute. So you might think, you might call that not commutative. Okay. But it doesn't commute in a specific way. The way it doesn't commute is if I change my mind about this arrow, beta being the block permutation of A many and B many things past each other, now this diagram commutes. Okay. So I'll call this commutative, co-commutative-ish. And we'll come back to that. Are there any questions about sort of what the phenomena that we've observed in nature? We don't really know what these phenomena amount to at all, but are there any questions about what we've observed? Okay, so so now I'm going to introduce some language that will let us call this something, as mathematicians love to do. So first of all, before we have any maps, what do we have? We have these spaces, right? We have a collection, we have a sequence of spaces, right? And the first thing we say about these maps is that they're equivariant. So we should have some language for a collection of things with actions. Okay. So we're going to call that a symmetric sequence. This has many names in the literature. Some of them include species, which is kind of an amazing name, and FB module, which is a drier name. I'm going to use the older symmetric sequence. So it's a collection. I'll call the whole thing curly X, but it's a collection of countably many things of whatever kind you want. So perhaps they are spaces, perhaps they are vector spaces, modules, what have you. Okay, you can talk about symmetric sequences in any of those places. And what makes it a symmetric sequence is that the kth one carries an action of sigma k. And a map of such is just a collection of equivariant maps. And of course, the example that we are most interested in is the example of the symmetric sequence of configuration spaces. So the kth space in that symmetric sequence is applying any functor to this collection of spaces produces a symmetric sequence in the target of that. So in particular, homology and cohomology. Okay. Which would you like me to explain? Oh yeah, so you're right. This is a little bit gnomic. So what I'm saying is I'm telling you the name of a symmetric sequence. The name of the symmetric sequence is f of x. And it is defined by saying that in weight or arity k, it's this space with its action of sigma k. Yeah. Does that answer your question? Great. Other questions? Yeah.
Can I think about this as like a functor from gamma op or something like that?
I think that gamma, I'm not one of the gamma people, but I think that's finite pointed sets. Isn't that right?
Yeah.
So not quite, but you can think of it as a functor from the groupoid of finite sets and bijections. Yeah, that's the same thing. Other questions? Okay. Another definition. I can take two of these things as long as I'm living in somewhere linear, like vector spaces, and not like topological spaces. I can tensor them together. So the tensor product symmetric sequences x and y is the following thing. So I want to tell you who a symmetric sequence is. And so what I have to do is I have to tell you who that symmetric sequence is in each arity or weight. Okay, well, what would I do if these were just graded objects? I would take, for every way of writing k as a sum of two numbers, I would take like A and B. I would take the eighth piece of this and the bth piece of that, and I would tensor them together. That's what I would do, right? So I would say sum over all the ways to write k as A plus B of the eighth piece of A tensored with the y piece of B, the B piece of Y. Yes. Yeah, so an FI module, we'll actually say something about FI modules in a little bit in slightly different language. An FI module is more structure than the structure of a symmetric sequence. So inside the category, so to bring everybody else along for the ride who hasn't heard of FI modules, FI is the category of finite sets and injections. And inside of that category is the category of finite sets and bijections. And so I can take any FI module and I can restrict it to get an underlying symmetric sequence. Other questions? Okay, so the issue is that this cannot possibly be a symmetric sequence, or it can't not. I mean, I could declare the action to be trivial if I wanted to, but that would be silly. There's no obvious action of sigma k, which has to act on the kth piece of the symmetric sequence on this thing, but there is an action of sigma a times sigma b, and then that means that there's a universal way to promote that to an action of sigma k, namely by inducing. So by induce from sigma a times sigma b to sigma k, now I have a sigma k representation. This is the tensor product of symmetric sequences. An example that will show you that this is the right or a reasonable idea. This is an example / exercise. The cohomology of the configuration spaces of a disjoint union is the tensor product as its symmetric sequences of the cohomology of the configuration spaces of one space with the other. So this is the tensor product of the cohomology of the configuration spaces of X with the cohomology of the configuration spaces of Y, where this tensor product is interpreted as the tensor product of symmetric sequences. So in other words, this cohomology of configuration spaces construction is a symmetric monoidal functor if I view it as valued in symmetric sequences. So this should convince you that this is a reasonable definition. If you're only convinced by category theory, and I'm sure there are some of you here, this is what's called deconvolution. So now you like it. But of course you knew that if you know what deconvolution is. Is there a question over here?
Is it obvious there's no sigma k action on the right-hand side, because you're taking the direct sum of all of those things, right? So a permutation would take A to some other A, wouldn't it?
So the issue, I want to agree with you, and the issue is that this is a partition of the number k and not the set k. If I could instead write, and maybe I should have, probably I should have, I could have written the direct sum over all set partitions of k of blah 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 without the induction, but then I'd have to have a slightly different convention of what a symmetric sequence is. Okay, whatever. And then what you're saying is accurate. So the induction is the thing that bridges the gap between partitions of number and partitions of set. Yeah. Other questions? Okay, so with all of that definitional investment, we can now, as Paul Gorse used to say when I was in grad school, we can make our confusion specific. So one more definition. A twisted commutative algebra is a commutative algebra in symmetric sequences with that tensor product. So in other words, it's a symmetric sequence, and it's equipped with a map from it tensor itself to itself that is associative, commutative in this sense. You can think about what the symmetry is between x tensor y and y tensor x. There is one. And unital. Okay. So anytime I have symmetric monoidal category, I'm entitled to think about a commutative algebra. I just need a commutative monoid, unital monoid. Okay. Everybody on board so far? If this feels like, as it sometimes can, enough words that you can't see what's underneath all the words, what a twisted commutative algebra is it's a graded algebra. So in other words, I can multiply something in the kth piece and the lth piece and get something in the k plus lth piece. It's associative in the normal sense. There is an action of sigma k on the kth piece of the graded object, which is not a usual thing that you have. The multiplication in the twisted commutative algebra is equivariant with respect to the smaller subgroup that acts as over here. And the commutative part is exactly that the two different multiplications are interchanged by the block permutation. That's it. That's all. It's a graded algebra with some equivariance conditions. That's all it is. This is just like a clean way to say that. And so the exercise is to unravel the definitions and show that the SABs endow the cohomology of the configuration spaces of any space. We didn't require it to be a manifold anywhere, with the structure of a twisted commutative algebra. So we'll abbreviate to TCA. Right. Questions so far? So far, all we've done is observed some maps in nature, and now we have an axiomatization of the induced structure at the level of cohomology.
So f of x is now all the f's together?
Yes. Yeah, it's this f of x, the symmetric sequence that associates fk to the number k. Yeah. Other questions? Okay. A comment before we move on to tie into something that I alluded to yesterday. If you have a twisted commutative algebra, you can look at the sigma k invariance at each level, and that's now a graded object because you've taken away the action. And you can think about why this is true. The twisted commutative algebra structure descends to a commutative algebra structure on that graded object. So you can take invariance and get a commutative algebra. And you actually get more than that, but that's fine. And that structure on the invariance is the same one that we saw yesterday on the collection of all unordered configuration spaces, on their cohomology. So we observed that the cohomology of the unordered configuration spaces of Rn rationally looked like it should be a polynomial ring tensor and exterior algebra, and it is. And the multiplication comes from this structure. Okay, so we've identified a topological source for what was just an algebraic coincidence that we had noticed yesterday. Okay. Questions? Okay. So now we know that the cohomology of the configuration spaces of any space is the twisted commutative algebra, and we know the cohomology of the configuration spaces of one space very well, or infinitely many spaces, Rn. So the question is, obvious question, which one is it? For that, let me give you a couple of exercises that, if you haven't seen this step before, it will be useful in sort of grokking the definitions. The free twisted commutative algebra, we can say what it is, generated by a symmetric sequence X. I'll call it sim of x. As an, I'm just going to describe what its underlying symmetric sequence is. As a symmetric sequence, it has a weight k piece for every k. And if you work it out, sort of from first principles, what you find is that it decomposes as a direct sum over partitions of k. The induction from sigma lambda to sigma k, the same sigma lambda that we met yesterday. And the tensor product over the blocks of the partition of the symmetric sequence evaluated at the block. Okay, so this is something you can write down what sort of a free object looks like in general in any reasonable linear place, and work it out, and this is what you will get. And this should look familiar to us. Yesterday, we wrote down the cohomology of the order configuration spaces of Rn, and we found a decomposition over partitions. And we proved that the L lambdas were induced from smaller pieces, exactly of this form. Okay, so the further exercise, which is not much more than this, is to show that in fact the cohomology of the configuration spaces of Rn as a TCA is the free TCA generated by the symmetric sequence that sends k to L of k, the same L of k as from yesterday. Right. So the answer to the question, which twisted commutative algebra is the configuration spaces of Euclidean space, is it's free. It's freely generated by this symmetric sequence, which isn't a new calculation from what we did yesterday, but it is somehow a satisfying one. Okay. Questions so far? Yeah, so this is my my homebrew notation for the symmetric sequence that in weight k is L sub k, the same L sub k as from yesterday. Okay, so if we have free algebras, in particular, we have free algebras on one generator, which we should think of as being, free commutative algebras. We have free commutative algebras on one generator, which we should think of as being the analog of a polynomial ring on one generator, which is the thing that we met. It's no longer on the board, but earlier in this lecture, we met the polynomial ring on one generator in inducing stability. So in particular, or maybe I'll write this on this board. Never mind. We consider the free twisted commutative algebra on one generator, which I will call script S. Why not? On what do I mean by on one generator? I mean, as my generating symmetric sequence X, I'm going to take the ground ring. I'm working in graded modules over some ground ring. I'm going to take the ground ring in weight k equals 1 and 0 everywhere else. Okay. So the ground ring R in weight 1. If you plug that description, the ground ring, with the trivial representation, the trivial action, there's only one action of sigma 1. So, okay. If you plug this symmetric sequence into that expression, what you will find is in every arity, in every weight, this free TCA is the ground ring. So it's one-dimensional in every weight. So it looks more like, well, whatever. Yeah, it's one-dimensional. Okay. Why do we care? Why do we care about that particular twisted commutative algebra? Well, it's something that we definitely know is acting no matter what. So what we can do is we can look at the unit in H0 of our space. X is the background space for the configuration space that we're considering. X, of course, is the same thing as the configuration space of one particle in X. This sits inside of the cohomology of that symmetric sequence, right? And so what this means is I have a canonical element in weight 1 of this TCA. No matter what X is, I have a canonical element in weight 1. And so by the universal property of a free algebra, that means that for any background space, I have a canonical and functorial action of S. It just comes to us. So via this composite, the target, the cohomology of the configuration spaces of X, becomes an S module. Really a graded S module because each homological degree separately is an S module. Okay, so this S module structure is like a shadow of the larger TCA structure. And the theorem of Tom Church is that if M is a connected manifold with dimension at least 2, then that S module is finitely generated. So if M is a connected manifold of dimension at least 2, then this S module is finitely generated. Okay. In each degree. Thank you. I forgot to say that the other time too. So I want to compare this to the theorem of Arnold and Siegel and McDuff. The hypotheses are essentially the same: connected manifold, dimension at least 2, except we've removed the hypothesis of openness, which is an improvement. We've lifted our discussion to the world of ordered configuration spaces. The stability theorem due to them was about unordered configuration spaces. Or at least as I phrased it, it was about unordered configuration spaces. And we've replaced the literal polynomial ring on one generator with this sort of twisted version of the polynomial ring on one generator. But otherwise, they seem like they're the same theorem practically. One comment before we go farther, comment in the form of an exercise. So the exercise is that so this like the other theorem, which was not phrased in the way that the authors phrased it, this is also not phrased in the way that the author phrased it. And so the bridge is given by this exercise. So the structure of an S module is equivalent to the structure of something that was mentioned in a question from the audience, the structure of what's called an FI module, so a functor from the category of finite sets and injections. And that's the language in which Church and his collaborators talk about this stuff. The reason I phrase it in these terms is that it somehow makes the parallel between this story and the older story in terms of the polynomial ring on one generator completely transparent, and also the parallel with some things I'll talk about tomorrow. Everybody on board so far? So what I would like to, yes.
So on the second exercise on the upper board there, you identified the left-hand side as a free object and some other thing. Is this specific to Rn, or does it generalize to some other configuration spaces? Like,
This is definitely specific to Rn.
okay, thanks.
I mean, it might be true for some other configuration spaces, but we know that in basically no other cases. So, yeah.
Do you know any other class of spaces apart from connected manifolds of dimension at least 2, where you have this theorem of Church? Finite stability complexes where every point is in a closure of a cell of dimension at least 2 or something?
Something like that might be known. I'm not sure. Louis probably knows. The kind of thing that I'm aware of is about the kind of thing that one can prove readily and very generally, as you know, of course, is about compactly supported cohomology of configuration spaces. So Dan Peterson has beautiful work that shows stability in the sense that I'm talking about for compactly supported cohomology of like anything, basically, configuration spaces of anything. And then the point is that if you're a manifold, then the configuration spaces are also a manifold, and you use Poincare duality. But in terms of actual homology, no, I don't know anything. Do you, Louis? Okay. Other questions? Okay, so what we did right after we learned about the finite generation result by Arnold and McDuff is we appealed to structure theory by Hilbert that told us about the asymptotics of the dimension under the assumption of finite generation. And so what we should expect is that this finite generation will also constrain asymptotics, and that's true. So what I'd like to do, hopefully I will have the time to do this in what remains. I'd like to tell you about how this constrains the asymptotics, and then I'd like to sketch a proof of the finite generation result, and then we'll probably be done for the day. Yeah. So I guess I'll go to a clean board. The structure theory that is analogous to the theory of the Hilbert polynomial is the following theorem of Church, Ellenberg, and Farb. Which says the following. How did I want to phrase this? So let's say we have a finitely generated S module. So a finitely generated module over this sort of twisted polynomial ring on one generator. And let's say that we are in characteristic 0. There are results outside of characteristic 0, but let's just stick with this for now. Then what we can say are 2 things. So first, we can say that the dimension of x of k as a function of k is eventually equal to a polynomial in k. So that's like Hilbert's result, except different in sort of a crucial way. Hilbert's result says that the Hilbert polynomial has degree at most the number of variables, right? And there's no control on the degree of this polynomial. Or like there is if you have more sophisticated knowledge about the module, but a priori there's no control over the degree. And the second thing, which is sort of the famous thing, or it gives this theorem its famous name, relies on a little bit of knowledge of the representation theory of the symmetric group, which I will black box. So you may know that irreducible representations of sigma k in characteristic 0 are classified by partitions of k. This is a different place that partitions show up than elsewhere. And so what I can do is I can look at a particular partition, lambda, and there's a way to take that partition and pad it to be a partition of any larger number or any sufficiently larger number. And then we can look at the multiplicity of the irreducible representation of sigma k in xk indexed by lambda. And that is eventually constant. So I'll walk through that again because it's a number of words. So I can choose a partition of any number, fixed, and I can sort of promote it to a partition of all larger numbers in a way that I'm not specifying because that level of detail wouldn't help. And then I can look in x of k for k unbounded, letting k grow. I can look at the multiplicity of the irreducible representation indexed by that partition. And as a function of k, that eventually becomes constant. So this statement rather than this statement is really more of an analog of Hilbert's result because constant is what Hilbert says about a polynomial ring on one generator, number of variables minus 1. So this is the same number of variables minus 1 growth phenomenon, just irrep by irrep instead of in total. Okay. So this result is what's called representation stability, or rather the second statement is what's typically called representation stability. Okay. Questions about any of this before we turn to outline of proof of Church's theorem? I'm not going to say anything about Church-Ellenberg fiber.
How are you able to go as far as this without mentioning braid groups?
I did mention braid groups. I mentioned braid groups on day 1. And then never again. I would have thought about saying more about braid groups, but I was informed that that would be taken care of for me. unfortunately, we will not hear much about braid groups this week, except perhaps some brave, I don't know, you've said that something will happen tomorrow morning. So maybe an intrepid soldier will give a blitzkrieg of knowledge about the braid groups tomorrow morning. Who knows? Who knows what will happen? Other questions? Volunteers. Okay, so so we want to prove that the cohomology of the configuration spaces of a manifold with these assumptions is finitely generated as an S module. That's what we'd like to do. And so, of course, the question that we must ask ourselves is, how would we know when an S module is finitely generated? So question, when is an S module finitely generated? There are probably lots of answers to this question, but I'm a simple person, and so I know only two good answers to this question. So answer number one, which is an exercise, is these, or rather, let me back up for a second. What's a good way to be a module over something? A good way to be a module over something is to be a ring with a map from that thing in, right? So a good way to be an S module would be to be a twisted commutative algebra with a map from S. A good way for that to happen would be to be a free twisted commutative algebra with a map, with a specified element in weight 1, right? Anytime I have a symmetric sequence, I can look at the free twisted commutative algebra generated by it, and if I pick an element in weight 1, then that produces the structure of an S module on the whole algebra. And so sometimes we can say that that thing will be finitely generated. That's a particularly easy case. So if X is a symmetric sequence with the following properties. So in weight 0, it vanishes. In weight 1, it's the ground ring. In weight, sorry, what was number 3 going to be? Oh, yes. So I forgot one word that I think I keep forgetting. So I want this to be a symmetric sequence in graded modules, graded vector spaces. So this is a graded symmetric sequence. And so because X of k is a graded object, we can ask that it's a finite type. So finitely generated in each degree. Finite type. And finally, there's a sort of eventual vanishing condition. X of k is eventually 0 in fixed degree. So we don't sort of have infinitely many generators in a particular degree. Under those 4 conditions, the free twisted commutative algebra on X is finitely generated as an S module. Where it gets an S module structure from this condition, X of 1 being the ground ring. And this really is an exercise. You just have to look at this formula. You just have to interrogate it a few times and see that all but finitely much stuff vanishes. So in particular, Church's theorem about finite generation holds for Euclidean space because we saw that Euclidean space is free on something that satisfies those conditions. The second way that we know that an S module is finitely generated is the same way that we know that modules over polynomial rings are finitely generated often, which is using the theory-anity. So this is definitely not an exercise. This is a real theorem. So by another theorem of Church, Ellenberg, and Farb, the TCAS is Noetherian. So this is an analog of the Hilbert basis theorem for this analog of the polynomial ring. So finite generation is closed under the formation of subquotients. So finite generation is closed under formation subquotients and extensions, but extensions would be true no matter what. Quotients will be true no matter what. It's really just the subs. Subquotients. I want to stress that this is not automatic. Most twisted algebras, most twisted commutative algebras, or let me say it this way. I have no idea if what I was about to say is true. Many twisted algebras that you write down are not Noetherian, provably. Most twisted commutative algebras that you write down, even super reasonable ones, nobody knows how to prove that they are Noetherian. So this is a very, very special result. There's no general analog of the Hilbert basis theorem that is known. I think it is suspected to be true, but it is not currently known. So this is an actual theorem. Okay, so we have two tools at our disposal to prove finite generation. We can look at sort of sufficiently finite free twisted commutative algebras, and we can form subquotients and extensions. Those are sort of the tools at our disposal. Cool. And so the result that comes to our rescue is important theorem of Totaro, which is sort of the computational backbone of much of the subject. So let's say it this way. So for simplicity, I'm going to assume that the manifold is oriented. It's not, it's just to write something simple. So let's say that M is an oriented manifold of dimension at least one. Sorry, at least two, excuse me. Then what Totaro gives us is a spectral sequence which goes from the free TCA generated by what we get by tensoring the cohomology of the manifold with the symmetric sequence. I've erased it by now. I'm going to have to be sure to move this up. That's fine. With the symmetric sequence that puts LK in each arity K. So that's the symmetric sequence that we saw earlier, on which the configuration spaces of Euclidean space are free as a TCA. So these are the generators for Euclidean space. This is the contribution for the manifold. So this is what's beautiful about this theorem, is it sort of splits the problem into two pieces, at least in principle. In practice, you can't do anything with this, but there's like the manifold piece, and there's the configuration-y piece, but it's purely a Euclidean piece. And then what what ties those two pieces together is the spectral sequence. It converges to the cohomology of the configuration spaces of the manifold. Okay, and when I write this tensor product, this is obviously a symmetric sequence. I'm viewing this as a symmetric sequence concentrated in weight 0. So the only action of the symmetric group on 0 letters that there is, which is trivial. Okay, let me put the boards up. So there's a lot to say about this theorem, and most of it I will not say. I'll tell you where it comes from. So what Totaro does is he looks at the Leray spectral sequence for the inclusion of the ordered configuration spaces into the Cartesian power. According to this map, there is a Leray spectral sequence for sheaf cohomology of the trivial sheaf, and Totaro analyzes sort of what that push forward sheaf looks like, and most of the time, away from the fat diagonal, it looks trivial, and that somehow is why the cohomology of the manifold is showing up. But near the diagonal, it looks non-trivial because the diagonal is what's missing here. And somehow, when you get very near the diagonal, you are somehow like, I don't know, disappearing into the tangent bundle of the manifold, because that's a tubular neighborhood of the diagonal is the tangent bundle of the manifold, right? So when you disappear into the tangent bundle of the manifold and somehow use orientability in the Thom isomorphism, then what you're really looking at is like a configuration in the tangent bundle fiber, which is Euclidean. So somehow that's where the Euclidean part comes from. Okay, whatever. So this is the Leray spectral sequence for that inclusion. There are other ways to derive it, but okay. Okay, and so now Church's theorem follows, basically, because what you have to do to prove Church's theorem is first check that E2 is finitely generated. So check, which is easy, that this symmetric sequence that we're generating the TCA with satisfies those conditions, which it does. And then by closure under subquotients, that tells you that the infinity page is finitely generated. The infinity page is just the associated graded, but that means that the actual thing you care about has a finite filtration with finitely generated associated graded, and that's good enough. Okay, so maybe I will not write that and instead leave it at having been said out loud. Let me give just 2 more comments. Totaro tells you more than just the form of the E2 page. He tells you the form of the first non-zero differential in terms of the cut product in cohomology of the manifold. There are higher differentials in general. But in characteristic 0, the invariant part of the spectral sequence collapses. And so what results is just a chain complex that calculates the rational cohomology of unordered configuration spaces of any manifold. So instead of a spectral sequence, just a chain complex. The collapse of the invariant part of the spectral sequence is something I proved. And with that, you can calculate the Betti numbers of configuration spaces of any surface. It's a very effective computational tool. Let me see if I wanted to say anything else. Let me write some problems on the board, and then we'll be done. So I would like to recommend a few problems to you, which will show you that we don't really know very much. So here are some problems. If you could tell me the Betti numbers of the ordered configuration spaces of the torus, I would love to know that. We didn't know the Betti numbers of the unordered configuration spaces of the torus until I calculated them now like a million years ago. But anyway. I would even accept, I would be excited about any stable multiplicity. So by representation stability, stably, this breaks up into sort of constant terms by partition, and we only know the trivial partition. That's the unordered configuration space. So choose any other partition. Tell me any stable multiplicity. Sorry?
Can you do the circle?
No. Dimension at least 2. Dimension at least 2. Yeah, and not Euclidean space or a sphere. Yeah. I would love to know the cohomology of the unordered configuration spaces of a closed surface with mod p coefficients for genus bigger than 0. We know like almost nothing about that. These are probably hard problems. I'll give you a problem that's a bit easier. The Betti numbers of the configuration spaces of complex projective space are only known for like n at most 3 or something like that. There should be some recursive thing that you can do using the chain complex that comes out of the spectral sequence, the invariant part. But we mostly don't know that. So as you can see, our knowledge is slim, because as soon as you put any interesting manifold in, suddenly we almost don't know anything. Okay. Cool. That's it for today. I went over a couple. Sorry about that.
Questions? More questions, that is.
Is the first problem interesting even for some particular K, or you only interested in general cases?
So it's known for K at most 5 or something. Louis, is that true? Yeah. Okay. So it's known for a few low values. Probably more interesting than the individual thing would be the stable calculation. We know the degree of growth of the Betti numbers as a function of K. That's a theorem of Roberto Pagaria. He has a conjecture about what the leading coefficient is. It would be interesting to know that. So really, like, kind of anything would be good. Yeah.
Thank you.
Other questions? How do you know? How do you know that the third problem is easier if it's not known?
Oh, this is something that plenty of people have thought about. There's like a complex. This spectral sequence collapses in the case of the torus, and so there's a complex that calculates it. It's just too big, and so probably if progress is going to be made on this, it would have to come by some other route than sort of the conventional tools. I have a program that is like aimed at it, but do I think it's going to get there? Not really. There isn't even really an approach. And I like maybe there's an approach through some like this has an analog over the sphere spectrum, and so you can do something over FP, but the information you would need to know about that is quite sophisticated homotopy theoretic information about power operations over the spectral Lie operad, or maybe partition Lie algebras, I'm not even quite sure. And even understanding the first page of that spectral sequence would be probably hard. And aside from something like that, I don't really know how you would come at this. There are methods for sort of open surfaces that have made some progress, like Andrea Bianchi and Andrea Stavro have a really nice paper about, I think, one punctured surfaces, but for closed surfaces, I don't think anybody has any idea what you would do. Here, there's just a chain complex that's a lot smaller than the chain complex here. In general, the algebra and combinatorics in the unordered case is a lot smaller than in the ordered case. And I somehow have the sense that nobody has like pushed hard enough on this because I don't know, maybe they didn't care enough or something. I don't know. We also didn't have the calculation for surfaces rationally until my collaborator and I sort of rolled up our sleeves and decided we were going to be obstinate enough to do it. A lot of people are satisfied with the chain complex. They're like, I have a chain complex, that's a computation. And I disagree. I don't think that's a computation, but I think that attitude maybe has contributed to this not being attacked with fervor, you know, and the absence of a direct application.